Welcome to the final block of the architecture sandbox. By now, you've realized the defining reality of our AI platform. The data never stops flowing. We aren't dealing with static, finite databases anymore. We are dealing with an unbounded, infinite stream of binary audio chunks and JSON telemetry that constantly hammers our ingestion layer. And while the incoming data is infinite, our physical hardware is not. Our streaming workers are strictly bound by finite memory buffers and a strict, non-negotiable latency budget of under 800 milliseconds. To survive this mismatch, we must introduce an architectural mechanism that mathematically slices infinite streams into finite, actionable blocks. We call these windows. These windows are the prerequisite for our system to make sense of the chaos. Without them, we cannot calculate usage metrics, detect platform abuse, or trigger systemic alerts. Our objective today is to lock down our streaming boundaries. To accomplish this, we will need to completely master three distinct grouping strategies: time-driven windows, activity-driven sessions, and time domains. Bounding infinity provides the survival mechanism required to prevent widespread memory starvation across your distributed workers. Let's start with the first tier of stream partitioning: time-driven windows. These are data groupings governed entirely by strict temporal boundaries. The tumbling window partitions time into rigid, non-overlapping blocks for efficient, low-stakes aggregations like billing. But this creates a boundary blind spot where edge events split and fail to trigger alerts. A hopping window fixes this by overlapping blocks with a smaller advance interval. We map hopping windows directly to operational dashboards. They provide engineering teams with a smooth, rolling view of system health, without the extreme processor overhead of tracking every single event individually. But sometimes we need absolute per-event granularity. For that, we use the sliding window. For a sliding window, rigid blocks disappear. As each individual data point drops, a unique window bracket spans outward, anchored to its exact timestamp. This creates instantaneous tracking, but maintaining these dynamic bounds demands maximum memory utilization. Because of that cost, we reserve sliding windows exclusively for high-stakes defense mechanisms, specifically enforcing API rate limits at our public gateway. If a malicious user attempts to flood the system, a sliding window catches the API limit breach instantly. It triggers an HTTP 429 response, cutting off the flood before it can degrade our sub-800 millisecond latency budget. Ultimately, selecting a time-driven window is a direct mathematical compromise between how much system memory you are willing to burn and how accurately you need to detect a threat. Strict time heuristics work well for system metrics, but user behavior doesn't neatly align to a 5-minute clock. For that, we pivot to dynamic, activity-driven grouping. Session windows use horizontal swim lanes labeled by call IDs. Incoming data is strictly routed into its corresponding lane. The session expands organically with user activity, extending through brief pauses, and terminates only when an empty space exceeds an inactivity gap threshold. The core architectural dilemma here is tuning the exact duration of that inactivity threshold.
If we close the window too aggressively, a user who simply pauses to take a breath gets cut off, and we end up processing a fragmented, split transcript. Conversely, if we set the gap too high and leave the window open waiting for a user who has already hung up, we pin critical memory on our streaming workers and precipitate system starvation. Implementing activity-driven session windows effectively requires us to perfectly align hard mathematical thresholds with the highly unpredictable cadence of natural human conversation. All of these windowing strategies assume data arrives cleanly. But out in the wild, we have to contend with the chaos of distributed networks, mobile buffering, reconnection drops, and routing latency jitter. This creates the time domain paradox. On this split-screen timeline, the top axis shows the client device generating a neat, sequential 5-minute block of continuous data. But down below, the server axis shows those exact data points arriving entirely out of chronological order, separated by massive, unpredictable gaps. The time an event physically occurred is rarely the exact time our server processes it. To resolve this, we have to split our concept of time in two. First, there's event time. This is the immutable moment the action actually occurred on the client's device, embedded directly in the data packet. We strictly map event time to our billing and analytics systems. If a user speaks for 5 minutes on their phone, they are billed for exactly 5 minutes of compute, entirely ignoring however long it took those packets to navigate the network. Then there is arrival time, the precise moment a packet physically hits our system's ingress layer. Arrival time is strictly mapped to gateway rate limiting. The gateway doesn't care when the data was generated. It only evaluates the absolute volume of traffic hitting the edge right now.
However, relying on event time to process stream aggregations introduces a critical threat. Notice how the session window on the server timeline is currently stretching infinitely to the right. It's waiting for a delayed packet that is stuck in a network gap. If we wait indefinitely, we will pin windows open and rapidly exhaust all server memory. To safely close these windows despite network jitter, we deploy a systemic safeguard called watermarking. A watermark is a mathematical delay budget. Watch the vertical line advance across the bottom timeline. It is tied strictly to the maximum event time our system has observed so far, trailing behind that leading edge by a fixed distance. The trigger mechanic is absolute. The exact moment that advancing watermark clears the upper boundary of an open window, the bracket snaps shut and immediately processes the trapped data. This explicitly bounds our acceptable delay. Any packets that arrive after the watermark has passed are deemed helplessly late and can be safely discarded or routed to a dead letter queue, saving the entire system from memory lockup. By combining defined window geometries with strict watermarking, we have officially locked down the persistence, ingress, and streaming boundaries of the platform. Now, the final task falls to you. Armed with these principles, log into the dashboard and mathematically define the exact watermarking delay budget required for late audio packets in our final architectural decision record. Let's finish to build.